Hey everyone, I hope you all are doing good. So in this lecture, we're going to be starting with graph terminology and we will also cover a theorem, right? So graph terminology basically means that we're going to be understanding the vocabulary that we use for understanding graphs, right? This is going to be involving like words like degree, what is adjacency, and incident, what does incident mean, and a lot of other stuff, okay? So let's start with understanding adjacency first. What does adjacent mean? And then we will look at the example, right? So I'll explain each one with this example on this right side and explain it with the question as well. Okay, so adjacent basically means U and V are adjacent if the set UV is in the edges. In other words, two vertices share an edge. The idea is simple. Two vertices are adjacent if they make an edge, right? In very simple words. So let's just take a look at an example over here. So think about A, right? A is adjacent to C. A is also adjacent to B because there's an edge connected from A to B and edge from A to C as well. Think about C now. C has an edge from C to A, and C, B are also connected, C, D are also connected. So C is adjacent to A, C is adjacent to B, and C is adjacent to D as well, right? And for B, B is adjacent to A, C, D as well. Okay, so if I ask you this question, try to pause the video and answer all three of them. Okay, so what is A adjacent to? The answer is it is adjacent to B and C, right? So B comma C. Okay, what is C adjacent to? C is adjacent to A, B, and D. So it would be A, B, and D. Okay, and what is E adjacent to? So E is over here in the graph, right? It's very below. But if you look at this carefully, right, it's not connected to anything, meaning it is not, the answer to this would be nothing, right? Because it's adjacent to nothing. So very simple word to understand. You should just know adjacent basically means that if it makes an edge or whatever it's connected to, it is adjacent to it, right? So A is adjacent to C and B, B is adjacent to A, C, D, and everything, okay? Now let's understand what does the word incident mean. Okay, let's understand the word incident now. So incident basically means edge E is incident with its two endpoints, U and B, right? Now, once again, this is very simple to understand. It's just that we are saying a edge is incident with its endpoints, right? So if we consider this edge AC, right? Think about this edge AC. It is incident with A, is incident with A and C, right? So the definition is, I think, probably a bit tricky to understand. Edge E, which is the set UV, is incident with its two endpoints, right? Just understand this word. Now, the trouble is in this question is the difference between what is adjacent and incident, right? This is the important difference. So adjacent is basically when you describe vertex to vertex, meaning I'm saying A is adjacent to C, right? A is adjacent to B. But if you talk about incident, it is edge to vertex. I'm saying AC is incident, the AC edge is incident with A, and it is also incident with C, right? The edge BC is incident with B, and it is incident with C, right? So adjacent, just always remember this, it's always defined vertex to vertex, and the word incident is defined edge to vertex. Now, probably these definitions might seem useless for now, and I think it pretty much they are, but it's just that in a lot of the definitions and explanations that you might see in your exams or books or theorems, they might use these words, right? Adjacent and incident. And at that time, having an understanding of these words becomes super important. The biggest problem in graphs is not the understanding, it's more like the definitions, knowing the definitions and what they mean, right? So it's more like as you keep going on, the definitions keep on adding up the previous concepts in them. So knowing the previous concepts and what they mean, what the definitions are, becomes super important to understand. Okay, so I hope you're able to understand the word incident. It's basically just defined using an edge being incident to its vertex. Adjacent means a vertex being connected to another vertex. Okay, so I've given these two questions, so try to pause the video and solve them. Okay, so which edge are incident with B, right? This is a very simple question. So which edges are incident with B? Edge AB is incident with B, so this edge, right? This is one example. Another example would be this one. BC, another example would be BD, and the third example would be BF, right? Which edges are incident with A? It would be, I can say, A comma C and A comma B, right? So 4 for this one and 2 for this one, right? Okay, so I hope you're able to understand. Now let's understand the word degree. Okay, everyone, now let's understand the word degree, right? So once again, this is the most simple one, I would say. Degree is the number of edges incident with V, right? Or I can say the numbers of a vertex. So neighbors basically means it's pretty much degree is the neighbors. So A has the neighbor B and C. So A has two neighbors. If you look at B, right? B has A, C, and D and F. So it has 4 neighbors. So it's pretty much the count of neighbors. Or in other words, what you can say is it's the number of edges incident with V. It's just like 2 different ways to say the same thing. Okay, but all you have to do is if somebody asks you find the degree of this vertex, it's just that you have to count what it's connected to, right? Okay, so I've given this question, find the degree of every vertex. So try to pause the video and solve this question. Okay, so let's solve this quickly, right? A has the degree 2 because it's connected to C and B. Let's take a look at B now. B is connected to A, 1, C 2, D 3, and F 4. So B is going to be 4, F is going to be 1, right? E and G are going to be 0 in this case. D will be B and C, so that will be 2, and C is going to be 3, right? So I hope you're able to understand this question. Okay, now there's also very important special cases that you need to understand. The first one is an isolated vertex. It is connected to nothing, right? So any vertex which is connected to nothing would be isolated. So if I ask you this question, which ones are the isolated vertex? It's going to be E and it's going to be D as well, right? These two will be isolated. Okay. Now, if I ask you another one is, what is pendant, right? So pendant, it has exactly one connection, which is the degree is 1. So if you look at this example over here, there's only one. F is going to be a pendant vertex, meaning it has only one connection, right? So I hope you were able to understand all these concepts. Now let's understand the terminology of a directed graph. Okay, everyone, let's understand the directed graph terminology now. Now, this is once again important, but very easy to understand. Okay, so in a directed graph, an edge is the tuple UV. Now, once again, this is a tuple, this is not a set, right? UV is not equal to VU. I think this is very important to know because in this time, we're going to be having arrows, right? Okay, so the terminology is U is adjacent to V. It is written as U is U arrow V, right? Now, it can also be written as that V is adjacent from U, right? These two are the same thing. It's just 2 different ways to write it, okay? So, U is adjacent to V is same thing as V is adjacent from U, just like a very minor detail to keep in your mind, right? Okay. Now, thing is, in a directed graph, each vertex has 2 types of degrees, right? So far in directed graphs, you just know a degree is all its neighbors. But in a directed graph, the problem is that A could be connected to B or C, it could be multiple, but maybe B is not connected back to A, right? So that's why you need 2 different types of degrees, right? So in this case, we have 2 degrees which are in degree. In degree is the number of edges coming into V, right? So in this case, in A's case, all the edges that have an arrow coming towards A will be the in degree of A, right? Okay, out degree is the number of edges going out from V. So whatever edges are going out from A are going to be the total number of out degree of V, right? So once again, very easy to understand. Okay, so first of all, I've given this example over here. For this graph, let's first find the total number of edges, right? So in this case, now this is a directed graph. So A to D would be different from D to A, right? So it needs to be counted differently. So we have A to D, that's 1. We have A to B and B to A, that's 2, and A to C and C to A. So it would be 1 plus 2 plus 2, which is equal to be 5. Okay, now I want you guys to pause the video and try to find the in degree and out degree of each of the A, B, C, D. Okay, Let's start with finding the in degrees first. What's the in degree of A, right? In degree of A would be 1 and 2. Okay. What's the in degree of B? There's only A going towards B, so 1 arrow. For C, there's only 1 arrow going from A to C, so that's 1 again. For D as well, if you look at it, there's only 1 arrow going from A to D, so 1 again. Okay, let's talk about the out degree now for each element. For A, the out degree is, first A goes arrows from A to B, A to C, and A to D as well, right? So we have 3 in this case. Okay, what's the out degree of B? It's just going to be 1. What's the out degree of C? C is going to be 1 as well. And what's the out degree of D? It's just going to be 0, right? Because D is not having an arrow towards anything. Okay, now what I want you guys to do is try to think about this, right? What happens if you add all these together? If you add the in degrees and the out degrees. So let's take a look at this, right? Okay, if I add all these together, I would get the total 5, right? And if I add all the out degrees together, I would get 5 as well. So this is one of the important problems to understand, right? The in degree is always equal to the out degree. The idea is that for a given graph, right, the total number of in degrees would be equal to the total number of the out degree for the entire graph. For any given vertex, right, you could have different degree. The out degree can be different from the in degree. So for example, A, in degree is 2, but the out degree is 3, right? So that's allowed. But the point is, for the entire graph, if you add up all the in degrees of all the vertices, and if you add all the out degree vertices, they would basically be equal. Okay, now let's understand why exactly this is happening, right? This is a very logically simple thing to understand. What happens is, whenever you make a point, right? So let's say I make a point from A to B. Let's say I make a graph, right, which is just simple A to B. What I'm doing is, I'm giving A out degree of +1, right? Out degree +1. I'm giving A out degree of +1. But if you think about this, right, I'm giving B a in degree of +1 as well. So every time I make a H, right, or every time I make a connection, let's say A to B or whatever it is, every single time I'm adding a +1 to out degree and I'm adding a +1 to the in degree as well. And that's why the total count always remains same. Now this is just a small concept to understand. You could have like a quiz question or maybe a tricky question where you might need to know that the in degree and the number of out degree is basically the same thing. Okay, now let's move on to the next topic. Okay, let's understand the handshaking theorem. So in an undirected graph, the sum of the degrees, so V over here represents like one vertex. The sum of the degree of all the vertices is equal to 2 multiplied by the number of edges. Now this is very important property to understand, or I should say very important theorem to understand. The idea is very simple. If you add up all the degrees, right, degree meaning whatever the neighbors are. So let's say I have this A to, let's say I have A to B. A has one neighbor, so A's degree is 1 and B's degree is 1 as well, right? If you add up all the degrees of all the vertices, it adds up to 2 multiplied by the number of edges. Now, once again, this has a very logical explanation to it. The idea is, take any edge UV, right? It adds +1 to the degree of U and +1 to the degree of V. So take a look at this example, right? This very simple graph. If you find the degree, right, this is just one edge. So you have edge A, B. Now this edge adds a degree to A as well and adds a degree to B as well. So in total, it gives you a degree 2, right? So, and that's exactly what this proof is saying. So it's saying take an edge UV. It adds +1 to the degree U and +1 to the degree V. So the total contribution is 2. Now do the same if you have a bigger graph. This will keep on happening. So let's say if I had another to C as well. Now I have this AC, right? So my degree would be 2 plus I have 1 degree of A, another one, plus 1 to C as well. So my total would be 4. So whatever the number of edges are, the sum of the degrees would be double of it. Okay. Now let me quickly try to explain it with the animation as well, just for a quick overview. And then we have another property that I wanted to explain with an animation. And after that, we will be giving some practice questions. Okay, guys. So let's say we have these 5 vertices and we have the 5 edges, right? So each vertex has a degree counter starting at 0. Yeah. So let's just watch the running total for this one. Right now it's 0. But if you look at this, right, for each edge, we are adding a plus 1. So for AB, plus 1 to A and plus 1 goes to B as well. Same for C, plus 1 to A, plus 1 to C. So if you look at this carefully, right, the pattern is that for every single edge, you're adding plus 1 to both the vertices in the edge, right? And since you're adding basically 2 times to each single edge, that's why the running count is an even value. So now in the end, we have 10 as the running total, which is pretty much 2 plus 3 plus 2 plus 2 plus 1, which is 5 times into 2. Right? So I hope you're able to understand. Once again, the point is very simple. For every single edge, you're adding a plus 1 to both the vertices. That's why it results in the degree equal 2 times the number of edges. Okay, guys, before we move on, I wanted to talk about this very interesting property as well. The property is the equal degree property, right? So I've given this sentence on the board. Just try to read it once and then I'll explain it. Okay, so the idea is in any simple graph with the number of vertices greater than equal to n, there are always at least 2 vertices with the same degree, always, no matter how you draw the graph. Now, this seems to be a very strong claim. Let's just understand what this means. They're pretty much saying that if you have a graph where the number of vertices is greater than equal to 2, so let's say a graph may be AB, or maybe you could have ABC, anything, right? But it has to be more than 2 or more than that. The idea is that you would have at least 2 vertices with the same degree, and no matter how you draw the graph. Once again, we are talking about a simple graph over here, right? Okay. Now, this seems to be a very strong claim, right? You might think that if we draw enough vertices, we might be able to draw all the different vertices with different degrees, but that is going to be impossible. There will always be at least 2 vertices which would have the same degree. So I'm going to try to prove this with an animation using the pigeonhole principle. So now let me show you guys the animation. Okay, so according to the theorem, in any simple graph with n at least 2, 2 vertices always share a degree. So let's just quickly understand why. I've given this graph on the right hand side, right? Okay, so every vertex has some degree between 0 and n minus 1. It can't connect to itself, right? So for n equal 5, that would mean that's 5 possible values, 0 to 4. So 0 means isolated and 4 means connected to all. Now the question is, can a graph have both an isolated vertex and a vertex W connected to all? So let's just take a look at this graph on the right hand side, right? So if W needs degree 4, but it can only connect to 3 if U is isolated, right? That means there's a contradiction happening. So try to pause the video and understand. So what this means is that at any point, right, if you have 5 vertices, then only 4 possible degrees are there. You could have 1 to 4, right? That's the pigeonhole principle, if you remember from the last lectures we covered. It's kind of like you have 5 pigeons and you have 4 boxes. So the fifth pigeon has to share. So 2 vertices pretty much have to share a degree. So hence the proof, which is any simple graph, always 2 vertices of equal degree. Okay, everyone, I've given these 3 questions on the board, so pause the video and try to solve them. Okay, so before I start, I'll quickly explain what the degree sequence word means. I'm sorry if I didn't explain it earlier, but the idea is very simple. Degree sequence basically means you're writing down the degrees of all the vertices in a non-increasing order, right? So this could be the degree of one of the vertices, then the second and the third, then up till all of them, right? It's just in a non-increasing order. Okay, So we have been asked to find the missing degrees possible. Okay, so let's just think about this, right? We're going to use the handshaking theorem that we just proved. The idea is we have been given that it has 10 edges. I know that the sum of the degrees is equal to 2 times e, which is equal to 2 times 10, which is equal to 20, right? So the total should be 20. If you add all of these together, this would be basically 16. So I'm missing 4. So 20 minus 16, this would add up to 16. And if I subtract it from 20, that means we have 4 left, right? Which means the count of 4 degrees left. Okay, so think about this now. What are the possible endings that we can have? I think one is you can end with 3 comma 1. So maybe the second last one has degree 3 and you could have degree 1, right? Another one possible is 4 comma 0, right? And the third one possible is 2 comma 2 as well, right? So I hope you were able to understand this as well. Okay, now let's move on to the question number 2. Can there exist a simple graph with 5 vertices and the degree sequence over here? Okay, so they're just asking this question, do you think this graph can exist or not? Now, let's just add up all the degrees together first. If you add these, you get 3 4 the 12th. So multiply by 4 plus 1 equal 13. Now, this is an odd number. Now, think about this, right? According to the principle, handshaking principle, the number of degrees, the sum of degrees is supposed to be 2 times the number of edges, right? Now, if you 2 times anything, it would be an even number. But this says the degree is actually an odd number, right? The sum of the degrees is an odd number. So this graph cannot exist. Okay, last one. A directed graph has the edges AB, AC, BC, CA, and CD. Find the degree minus and the degree plus. I'll leave it this one for you guys to solve. This is pretty much that all you have to do is just find what edges are going into A and what are going out from A. And I think that's very simple concept to understand. Okay, so that was pretty much it for this lecture. I hope you were able to understand everything that we covered. Once again, the graph lectures are not very difficult. It's just that they have a lot of definitions, I should say, which become very important to remember. Okay, so that's it for this lecture, and I'll see you guys in the next video.